All right. Hello, everybody. Welcome back. Today we are talking about Unita's lemma, and then limits and colimits. That's going to be the whole point of today. Yeah, Garrett, I guess is still asleep. It's like 7 in the morning here, so um, yeah, it just works how it works. So we're gonna go through exercise 1.2Z. Um, And we're just gonna kind of talk through it. I think because I told everybody to do it on their own. Um, so this is basically proving Unita's lemma. And then we're gonna go on to limits and colimits in section 1.3 of Vakil. So, okay. Recall that Unita's lemma says basically that you can recover objects in a category by knowing the maps into them. And that basically, moreover, if you have a functor which describes those maps, you can describe the category. Um, so, making a new document for lecture 11. Okay, so exercise 1.2.z A says let A comma B in ob C, or I guess we'll give it a script C. Um, give a natural bijection um, between um, HA and HB of covariant functors from C to sets and morphisms from A to B. No, B to A. Okay, so this shouldn't be too bad. Um, so we're recalling that HA is the thing, which is the representable functor. Um, and so basically, the setup is that let's see, what's the superscript mean? Superscript means that it's a covariant functor. An example 1.1.4. Oh, okay. He's doing the weird thing where he references ahead. Um, I think. Nope. 1.1.14. Okay. So we're defining HA is a functor from C in the sets with HA of B equals the morphisms from A to B. And HA of F, which is in the morphisms from B1 to B2 the morphisms of A. B1, F define B1. Oh, wait. um, I guess it's really the better way to express this is just going to be with arrows. It was not meant to be. Um, okay. So basically, it just kind of makes sense. Garrett's gonna be here in a second, and I need to do something real fast. So I'm just gonna mute my mic, turn the camera off for a second. Okay. Let's see. Yeah, Garrett just texted. Okay. So yeah, then basically we want to show that there's a natural bijection between these things. Um, of covariant functors. I mean, this just kind of is by construction, right? Like, if you have two objects in the same category, then the representable functor, HA, gets sent to the um, same class of morphisms. And then alternatively, their their subcategory of functors like also does the same thing. So if you have a morphism from B to A, then more AB gets sent to more AA. That is definitely a natural isomorphism. Yeah. I think that satisfies it just in terms of like what is this saying? So, oh, hey Garrett.
Hey, Tim, I'm sorry. My alarm didn't go
No,
off.
no worries, man. No worries. So we're going through the Yonetta's Lemma stuff. I waited just in case you were getting up,
Yeah,
so I
thank you.
started at 7:30. You haven't missed much. A lot of it's been writing down stuff. Um, so this is kind of the first third of Yonetta's Lemma, um, which is basically given a natural bijection from representable functors HA to HB, which go from the category to the category of sets, and then morphisms from B to A.
Yeah,
Um, then basically show that we have a natural, and it just kind of works out and makes sense.
yeah.
You can, if you want, watch the lecture, but honestly, I don't think it's super important.
Okay.
Um, um, yeah. So Yonetta's lemma formally. Um, Let f be a covariant functor from some category C to the category of sets, and let A in C um, there exists a bijection um, between the natural transformations HA to the functor F um, and the image of the functor of A. And so keeping in mind what HA does, HA sends objects to its morphism class. Um,
Hmm.
and then it sends morphisms um, to this, which is like the morphism class of its domain to its morphism class of its codomain. Um, and so we can see that that entirely describes the category. And that's the same thing that a functor does, right?
Hmm.
Um, so just kind of as a remark, um, given a category C, we can produce an induced category of functors of C where ob functors of C, hopefully my notation is clear here, um, consists of contravariant functors. Um, and those go from C to sets. And morphisms are natural transformations of such functions. Um, that looks like an E, doesn't it? There we go. I don't know if that's any better. Yeah. And then really Yonetta's lemma says that there exists a functor H in ob F of C that looks like a phi. Oh my goodness. I can't draw. I can't write.
Huh.
I hope you know whenever you see an E, it could be a phi, a C, a phi,
Oh yeah.
um
Or the Hebrew letters that you were going to.
yeah. H and ob C, where H goes from C to the functor category, F of C, which sends A, capital A, yes, to HA. And then Yoneda's lemma says that this is fully faithful. H is fully faithful, meaning that it's an injective and surjective
All right.
functor. Um, and is called the Yoneda embedding. And yes, the joke here is that the Yoda embedding, contravariant it is. Anyway. Anyway, so moving on from from the section. Wow, I really cannot write today. So limits and colimits. Um, and so this is one of the sections that has actually confused me for a little while. I keep thinking I understand it. I keep not entirely understanding it. So, um, yeah. Okay, starting off with some definitions. So, a category is a small category if the objects form a set. Um, and morphisms form a set. Um, and then let script F um, be any small category. Um, and script C be any category. Um, then a functor F from script F to script C um, with an object AI in C for each I in F um, at appropriate it commuting morphisms um, dictated by F um, is called, finally finishing the definition, um, a diagram indexed by script F. Furthermore, F is an index category, um, and is usually a partially ordered set. Um, in which, in particular, there is at most one morphism between any two objects. At most one morphism between any two objects. Other examples are sometimes useful, but um, and just as an example, let square, I kid you not, that's the notation used,
Oh wow.
be the category um and A is some category, um, then F from square to A is precisely the data of a commuting square in A. Um, and then we define the limit of this diagram. This is the definition for like the whole section. um, then the limit over F of AI, and this is really called the inverse limit. It flows the opposite way that it says it does. The inverse limit over F is an object of C with morphisms that basically follow down from the chart. So it goes to like the last thing, basically. So like this is the limit of this diagram.
Oh, okay.
Um, yeah, so the limit of the diagram is an object of C, completely breaking the example above.
Hmm.
Um, with morphisms um, Fj from lim AI over F um, to Aj. Um, so yes, that is defined from the limit to the j thing um, for each j in F, meaning that the limit is the final object. No, it's an
Okay.
initial object. It's an initial object.
That makes sense.
Maybe that's where the inverse comes from. um, such that if M from J to K is in the morphisms of F, um, then the following diagram commutes, and oh my God, this is a two-paragraph definition. Lim AI inverse limit over F to AK FK AJ FJ functor M commutes and the object and maps to each AI are final. Another word that they're using for this now is universal. Um, with respect to this property. Um, so more precisely, oh my God.
Hang on, can I get this
What is,
definition down real quick?
yeah, yeah.
Just the last
Um,
part of it, sorry.
let me just read through the more precisely given than any other object W with maps to AI commuting with the functor of M. What the fuck is M? Oh, M is an object. No, M is a morphism from J to K in the indexing category. Um, then GK is the function composition with a unique map from W into the limit. If the limit exists, it's unique up to unique isomorphism. Okay. All right, let me know when you're all good.
I'm good.
Okay. So, more precisely, more precisely, um, given any object W in what category? I guess the category that AIs are in. AIs are in OBC. Given W and OBC with maps, GI from W to AI, commuting with the functor of M, where M is from J to K and F. Um, and F is some functor into C. Um, um, i.e. gk is equal to f of m circ gi, then there exists a unique map g from w to the inverse limit over f of ai such that gi is equal to fi circ g for all I. Um, so this is kind of the better way of thinking about it, right? So the limit of AI is, or the inverse limit of AI is what I like to try and distinguish it because there's this other thing that we're going to talk about called the co-limit that goes the
Okay.
opposite direction. It's error reversing.
Oh, lovely.
Yeah, and so they totally named things backwards because this is the thing that does the thing that you would think that the limit does, and then the
Yeah.
co-limit does the thing that you would think that the error reversing of the thing called the limit does.
Yeah, I
Um,
figured as such.
yeah, because I honestly can't tell you why. Maybe we'll figure it out.
I've learned to realize mathematicians aren't good on logic. It's usually, in statistics, the right-handed, left-handed skewness, it's like goes the other
Yeah,
way.
yeah. Well, hey, that list includes you now. You're doing category theory, so
Oh, yeah, I'm sure.
um, but yeah, okay. So we're taking any object in our category C with maps into AI that commute with the other maps that are indexed by the category F, gives us a unique map into W, um, or from W into the limit of AI. So if we have
Yeah.
maps into AI, the limit of AI is something out of W.
Yeah.
And so here's where an example is worth 1,000 words, and a familiar example. Um, so products.
Okay.
um, Let script F be the poset, which is the arrow reversing of products. Um, then uh, then we obtain the fiber product. So like basically what we're saying is if we have a category C and we have a functor from script F into C, um, with F as an index, then the inverse limit of any AI over F in C is the fiber product through AI. And then as a second example, the script F is the isolated poset. Um, then we obtain product. Give me just 1 second. I need to blow my nose. Okay. So, um, a limit is really like with all of this notation. I want to add that a limit is really just a way of generalizing things like products, equalizers, and pullbacks. Um,
Yeah.
like when we're talking about the inverse limit of, something indexed by this poset, we get the fibered product. Um, if we just have the two things, then we get the product. Um, it is the thing like you can kind of picture lim AI kind of flowing like that, or like
Yeah.
lim AI. And as long as the AI piece is actually indexed by the yellow poset or the orange poset respectively,
Mhm.
then like the limit is the thing that flows into both.
Okay. That makes
Um,
sense.
yeah. And so like the terminal object, like the final object,
Yeah.
is the limit of an empty diagram, since everything flows into lim AI.
Yeah.
Um, yeah.
Yeah.
So, yeah. Um, okay, as a reality check. So, literally the next exercise is a reality check.
Really.
Yeah. So, exercise, um, reality check.
Nice.
Um, let E be initial in a category F, um, which is a poset. Um, show that the limit of any diagram indexed by script F exists. Oh no.
Shh.
The one after this, you remember the horrible base change diagram from yesterday's
Yeah.
lecture?
That's coming
Oh,
back.
we have to prove it again.
Oh.
Oh, this is gonna be a few lectures in this section.
Oh.
I think I'm gonna title this lecture Much Ado About Limits.
That's a good one.
Yeah.
Or
So
just the
we'll try and get through this reality check today and then the base change diagram.
go the base change to Doom part two.
Yeah. And then we'll start up our next lecture with formal power series. and the p-adic integers,
Okay.
and then colimits and filtrations and yeah. Okay, so let E be initial. So since E is initial in F, then for every AI um, with an index F, well, let's pull this out. So the AIs are indexed. We have an initial thing. All of the maps GI exist. Um, there exists a GI as defined here from W to AI. Commuting with the functor of M,
Yeah.
which goes from F of J to F of K. And so um, GK is equal to F of M circ GI. Um, and then by construction, we have a map from W into the limit of AI. What do we call the map up here? G? Yeah. Um, and then such that GI is equal to Fi circ G. Okay. Call me dumb. What the hell is little fi?
It's up there a bit. It's a function from the limit of AI to AJ to I don't know.
Yeah, I know, right?
Hang on. It's somewhere in here. We wrote this down.
I don't think we did. I don't think it's in there. I don't see it in the book. Oh, nope, we did. It's from the limit of AI to AJ. I lied.
Oh yeah, I see it now.
Yep. So,
Wait, no, that's FJ.
yeah, that's what I meant.
Oh,
The limit, or so Fi goes from the limit of AI over F into AI.
so on that
Um,
diagram back up there, it's like the triangle one.
yeah.
There's FJ. Is that an I into AI?
What?
If you go up, it's right there.
Yeah.
The J's are I's.
I mean, yeah, you could fix I in the indexing set and get that you have the morphism from lim AI into AI.
Okay.
And so the thing that makes all of this work is that E is initials, so we're guaranteed the FI. and the G. Uh-huh.
Okay. Yeah.
And then that proves the claim.
Yeah.
So honestly, the reality check not terrible.
Mm.
I still feel like I don't have like the physical intuition for this. Um, I think I've said this before, but like for me, whenever I like get a math concept, there's always like a physical like
Yeah.
kind of
Right.
like I don't think I have that yet. That's what more exercises are for.
Okay.
All right.
Did
Oh
you
yeah,
finish writing it out?
yeah, I did.
Okay.
Yeah. So now for the diagram from hell. So yeah. I'm gonna call this a lemma. So
Honestly,
x1
this
fiber
one,
product y equals y fiber product through the diagonal morphism of y with x1 fiber product of z x2 um, is the limit through f of ai of the diagram, which is x1 y x2 z. So we know that if it were just this construction, we immediately get the fibered product.
yeah.
But since x1 and x2 go into y, which goes into z, then we can kind of separate out two chains like
Okay.
that look like flattening it down to this diagram, which we know gives us the fibered product.
Yeah.
Um, and so of course, like the fibered product, which is here, is the thing which gives us like that.
Yeah.
It flows from the top of the chain.
Right.
Um, and like that's just pretty clearly the fibered product of x1 and x2 through y. But then
Yeah.
showing that that is also the fibered product of y with its diagonal morphism through z requires us to build out the whole flowchart. So let's do that. Okay. x1, x2, y, z. Then we need y to go up to its diagonal morphism through z. And then we need the fibered product of x1 and x2 through z. And then we need the fibered product of y through Y fibered product through X fibered product. X1 Z product. And so then this goes from, so Y to the fibered product goes through, I think we called it mu yesterday. And then we have no, I was wrong. It goes like this. And then we have this and this. And this is the limit of the diagram. Because it's the limit of the diagram because it's the fibered product of the two fibered products of the subdiagrams.
Yeah.
So the limit of a diagram is the limit of the limits of the subdiagrams.
Yeah.
So remark limit of diagram is equal to the limit of the limit of subdiagrams. I think that makes sense. I think that's okay. That makes
Yeah.
sense to me.
Can I just draw out the thing? Could you just give me a second? Sorry.
I'm gonna blow my nose real quick.
Okay. Uh, all right. I think I got everything.
Awesome. Okay. So, we have another example of limits that follows from a definition. Um, and so let A be a ring. Um, we define the formal power series A x of x um, is the resulting ring a naught plus a1x plus a2x squared plus dot 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 dot. Um, where ai are in A, and then ring operations are obvious. Um, and then in the category of rings, this is a limit. Um, and um, and what that limit looks like is if you have your polynomial ring quotient the ideal generated by so and so into the polynomial ring generated by x squared into polynomial ring quotient x, then you have morphisms into each of these things from AX. So noting that these structures, like these are quadratic polynomials. These are linear polynomials. These are constant polynomials. Right. So basically like that when you're looking at the ideal
Yeah.
there. Um
Tim, what are the double brackets for?
um as far as I can tell, that's the thing that we use to know that it's a power series, meaning that it's a
Okay.
collection of the infinite sums in this
Yeah.
variable.
Okay.
If it were like a multiple list, it would be the collection of infinite sums in multiple variables and in multiple permutations of the variables.
Okay.
So
Thank you.
like A of, and that's a very good question. A of x, y is the series of sums, n equals 1 to infinity of ai, xi, or x to the I. Or sorry, a equals 0, I think.
Yeah.
Yeah. And then the sum, oh, these should be n's, an, x to the n equals 0 to infinity of b to the n, y to the n,
Mm.
and then the sum n equals 0 to infinity, and x to the n, um, y to the n.
Okay.
And actually, no, I'm wrong. It's a double sum.
Hmm.
n and j.
Yeah. Okay. That makes sense.
Yeah. Um, and so then the universal property of limits here gives us a ring morphism from our polynomial ring over X into its power series, notably this guy.
Yeah.
um, because constant polynomials are just A, right?
Hmm.
Um, and so as a remark, if A is the real numbers or the complex numbers, the map from A over X into the power series of X maps through the convergent power series. And we're going to use power series actually a lot because the idea of a convergent power, like
Yeah.
something being a convergent power series, gives us a lot of geometrical intuition in
Okay.
certain spaces that, like, yeah. Having convergent power series of polynomials gives us the ability to map this thing called spec A to
Yeah.
the geometry of the space, and spec A is the ring of the prime ideals of A.
Okay.
So, yeah. Okay. So as another example, example, the p-adic integers. So let P and Z prime. Um, uh, P-adic Z, which is often denoted ZP. But so is everything else, by the way. This is not mod P by any stretch of the imagination. Um, is of the form A naught plus A1P plus A2P plus, or P squared. Um, where 0 less than or equal to A naught less than or equal, strictly less than P. Um, um, they are a limit in the category of rings by, so lim over rings AI is equal to ZP because we have Z quotient P, the ideal generated by P cubed, into Z quotient, the ideal generated by P squared, into Z quotient, the ideal generated by P. Um, and then really these are like basically GF P P cubed GFP squared and then GFP, which we're familiar with in the summer.
Yeah.
Um, remark these two examples are completions of rings. Um, and then as a second remark, limits don't always exist, but it's easy to check if they do. Um, how if the objects of your category can be interpreted as sets with additional structure and that arbitrary products exist. So objects can be interpreted as sets with some structure, and then arbitrary products. Um, oh God, what is that? Oh, that's terrible. I'm looking at the next exercise. That's so much notation. Um, hold on. Let me Google something. Okay, I'm going to state this next exercise as a theorem, and then we're going to prove it with completely different notation because this notation sucks.
All right.
Um, yeah, give me 1 second to blow my nose.
Okay.
Okay. Um, theorem. The limit of a diagram in the category of sets um, is basically a universal object that represents the solution set to morphisms in the diagram. Or is a universal or final object um, which contains um, the solution set to morphisms. Really, this is like pre-images, right? And like that makes sense. If you have a diagram, it's just going to be all of the shared solutions between any two like top things. Um, this also works in modules and rings. Okay. So any questions on that?
No.
Okay. So then as a definition, um, colim AI over some indexing set F is the error reversed limit over AI. Um, um, yeah. So there's a joke here. Have you heard the saying that a mathematician is a device for turning coffee into theorems?
I've not heard that.
Okay, well, it's kind of like the running
Yeah,
joke is that, mathematicians are devices for turning coffee
right.
into theorems. A co-mathematician is a device for turning co-theorems into coffee,
That's pretty funny.
or into phi, because you got to remove the co.
That was a pretty solid one.
Yeah, it's a pretty good one. Um, so what's the intuition here? Well, okay, so if the limit of a diagram is a final object, then the co-limit of a diagram is an initial object. Um, whereas if,
Hmm.
well, hold on. Let me double check something. Ah, math stack exchange has a really good explanation. Um, so like an initial thought for this is limits suck things up, co-limits suck things down. Um, but this could alternatively um, be seen as co-limits glue parts together, make a whole, and then limits reconstruct an object from its shadows. Does that give a little bit?
Yeah, that does.
It's kind of like both are the easiest way to connect all of the objects and arrows into a single arrow and
Yeah.
like store all of the data. And so like the co-limit is the arrow forward version of this, and then the limit is the arrow backwards version of this.
Yeah.
Um, so as an example of a co-limit, the abelian group 5 to the minus infinity z of rational numbers um, whose denominators are powers of 5 is the co-limit for I in Z plus um, of 5 to the minus I Z. And this can be expressed as the co-limit of the diagram Z going into 1/5 Z going into 1/25 Z, and so on in the category of abelian groups. So does this make sense?
Yeah, hang on. All right. Yeah, it makes sense.
Yeah. And then just as a definition, um, the uh, the colimit over an index set I is called a coproduct, denoted like so. And this is just the dual of the notion of the product.
Oh,
Um, wow, we're actually making really good time.
yeah.
Um, okay. So definition, um, a non-empty coset is called, all right, we'll call it S greater than is filtered um, if for each X and Y in S there exists a Z such that X is greater than Z and Y is greater than Z. Um, More generally, a non-empty category C, no, F is filtered um, if one for every X and Y in F, there exists a Z in F and arrows um, with X in the Z and Y in the Z. And then for each two arrows, U from X to Y, and then V from X to Y, there exists an arrow W from Y to Z such that W circ U is equal to W circ V. And so the picture here is that X, Y, Z. Well, if we have two arrows, um, I guess, yeah, two arrows like so. U, V, W has a unique factorization. This is also sometimes called a filtered index category.
Okay.
So I'm going to give a few exercises. Um, that we don't have time to do so that we can start next time with adjoints. Um, so hold on one second. I gotta Google something. The category of sets. The colimit of a diagram of sets is the disjoint union of sets modulo and equivalence relation. Okay, so I'm gonna write down the theorems and then your exercise between now and Monday is to prove these.
Okay.
Um, so colim of a diagram in sets is the disjoint union of the sets modulo and equivalence relation. Um, um, so as an example, you can look at 5 to the minus infinity, like just as a motivating example. 5 to the minus infinity z is a good example of this if you treat it as a
Yeah.
set, not as an abelian group.
Okay.
Um, 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 this applies to the idea of categories. Um, theorem, localization of an integral domain over a filtered set is a colimit. Um, and I think those are the only two I want to assign. Okay, so just as a closing remark, he has a summary. One useful thing to informally keep in mind is the following. In a category where the objects are set-like, an element of a limit can be thought of as a family of elements of each object in the diagram that are compatible. And an element of a colimit can be thought of as an element of a single object in the diagram. Even though the definitions of limit and colimit are the same, just with arrows reversed, these interpretations are quite different.
Okay.
So does that make sense?
Yeah.
Okay. Um, yeah. Cool. All right. Next time we will talk about adjoints.
All right.
Go ahead and try and prove these two.
Yeah, what time on Monday are we meeting?
Good question. I will have to send out an email about that.
Okay.
Cool. All
All
right.
right.
See you, Garrett.
See you, Tim. Have a good day.
Bye bye.